We are now going to get into network analysis, and this brings us to the next concept, that is resistors in series. To understand what is the meaning of resistors in series, let us first try to see how a resistor looks like. So if you can see here on the right hand side, it is basically a cylindrical body that's made up of ceramic. It has colored rings, also called as colored bands. And if you see at the two extreme ends, you have these contact terminals. So these are terminals from where this resistor can be connected to a circuit. So now I've tried to show a two-dimensional figure of a resistor here at the top. So you can see one resistor here and one resistor here. And both of these resistors are connected in such a way that the ending point of one resistor coincides with the starting point of the other. And when resistors are connected in this fashion, they are said to be in series. Before trying to understand resistors in series in detail, there are a few important points that we should remember, which will help us in attempting numericals as well as some theory questions, give reason type of questions. So I have written down those points here. These are relevant for resistors or appliances that are connected in series. So let's read the first point. It says that if there are multiple resistors connected in series, and if you want to find a substitute for all of them, that substitute is called as equivalent resistance. So that can be found by simply adding the values of resistances of all of those resistors and then determining the answer, which is called as the equivalent resistance. So if I have two resistors like this in series, if one of them is 3 ohms and the other is 5, then the effective or the equivalent will be 8 ohms. So that is the point which is being conveyed here. Next, in such a combination, the current flowing through each resistance is the same. I'll be demonstrating this as well. So the point here is trying to tell us that if there are multiple resistors connected in series, if the current flowing through the first resistance is X amperes, the current flowing through the other resistances will also be of X amperes. And yes, one important point that I missed, when you're connecting resistors in series, the effective resistance becomes very high because you're actually adding the values of the resistances. Then point number 3 is also relevant from the numericals perspective. There are some questions where in the circuit diagram, and we'll be solving those questions, an ammeter will be shown and the resistance of that ammeter will also be given. By the way, an ammeter is a current measuring device and it is always connected in series. And since we just saw that in series everywhere the current is the same, so the current that flows through an appliance or through a resistance will be the same as the one that is flowing through the ammeter. And basically that is how the ammeter is able to measure the current that is flowing through that appliance. One important point about ammeters is they should have a very low resistance practically, because the ammeters are connected in series. And if the resistance of the ammeter is very high, that will cause the equivalent resistance of the circuit to increase, and this will force the current to drop, and thereby it will not help us in measuring the correct value of current. So for this, one should design ammeters with very low resistance. Ideally, or in all numericals where an ideal ammeter is used, the resistance of the ammeter will not be considered at all. It is taken as 0. Now we'll be seeing a demonstration on resistors in series. So this is our circuit construction kit, which I'll use as a demonstration for resistors in series. So let's take two resistors and connect them in series. So you can see starting point of one resistor is being connected to the ending point of the other so that they form a straight chain, and they are now forming a series arrangement. We will use a battery and we will also use an ammeter. And let's complete the circuit by using a set of connecting wires. We'll also use a switch. So basically the circuit is now complete. You can see these free electrons, they are not moving in any direction because they can flow in one direction only when there is a potential difference. So even though we've attached a cell here, but there is no potential difference because the circuit is incomplete, and the circuit becomes complete when I tap the key. Now the key is closed and you see there is a steady flow of electrons in one direction. By the way, the flow is indicative of electronic current, but the kind of current that we have in our syllabus is conventional current. So I'll just select the other option. As you can see, the direction has got reversed. So conventional current always leaves the positive terminal of a battery and it goes to the negative terminal. So it's flowing anti-clockwise. The reading of the ammeter says that the value of current is 0.45 amperes. Let us see how this value can be obtained. The first thing that you should do while solving any circuit is determine the total resistance that is present in the circuit. So here we have a 12 ohm resistor and we have an 8 ohm resistor. The cell is an ideal one, so no internal resistance. The ammeter is an ideal one, so zero internal resistance. And the wires are always assumed to have no resistance. That means the total resistance in this circuit is only 20 ohms. So let me write that here. Total circuit resistance is equal to 20 ohms. Now the total voltage is the voltage of the battery, and that is 9 volts. And we will be using V is equal to I into R to determine the value of current. So I is V by R. V is 9. The value of resistance is 20. And when you divide 9 by 20, you will get 0.45 amperes as an answer. So this explains how the value of current that is flowing in this circuit is 0.45 amperes. Now, one important thing that is worth noting here is, and which was already presented in the theoretical part, that when resistors are in series, the current remains constant everywhere. So here I've just installed the ammeter in one place. Let us see by taking another ammeter and by changing its positions, let's see if the value or the reading of the ammeter is the same. So I'll select this ammeter here. Let's place it here. See the value of current, it's 0.45. Let's place it somewhere else. Let me place it here. It is again 0.45. Let me place it here, 0.45. And let me place it here, 0.45. So irrespective of the placement of the ammeter, the reading of the ammeter will be the same. And this basically indicates that current does not divide in a series arrangement and it remains same. But the other important point is about voltage. In a series arrangement, it is voltage that divides. That means throughout the circuit, you will not find the same voltage. And let us see that. So let me take a voltmeter and let's connect it here across the ends of the battery. Basically, this is the way a voltmeter is connected. So we always use the word across. A voltmeter connected across a cell, a voltmeter connected across a resistor or across an appliance. And you can see the reading 9 volt. So it is reading the entire voltage. That means there is no internal voltage drop. And this is because the cell or the battery does not have any internal resistance. Anyways, the point here is the total voltage that is being distributed in this circuit is 9 volt. And the only other place where we can see the consumption of this voltage is these two resistors. Voltage is only consumed across resistors. And if the resistance is 0, there cannot be any consumption of voltage. So internally, there is no resistance. So no voltage can be consumed inside. This ammeter also is an ideal one. So 0 resistance, hence 0 voltage consumption. So let's take the voltmeter and connect its LEDs or terminals across this resistor. And you can see it is showing 5.40 volts. That means the voltage that was being distributed in the circuit is 9, but the moment you bring the voltmeter and connect it across these two the ends of this resistor, the voltmeter is not reading 9 volt, it is reading 5.4. Similarly, when I place the voltmeter here, again, it will not read 9 volts, it is reading 3.60 volt. So now there are only two places where voltage can be consumed. So I'm going to place the voltmeter only here. And now let us see the total voltage that was given by the cell was 9 volt and the total voltage consumed. So let's use the same reading again. Here the total voltage consumed is 3.60 volt and that is being consumed by the 8 ohm resistor. Now let's take it back to the 12 ohm resistor and let us see the reading. It is 5.40 volts. Now let us add both of these values, 5.40 and 3.60, and you will get the same 9 volt back. So 9 volts was given by the cell and it was distributed across the two resistors, and you can see the voltage is different. It is not 9 volt. Therefore, we say that in series, the voltage differs and the current remains constant. Now, if you want to know how we got these values, so the calculation also can be shown. Once again, we've got to use the formula V is equal to I into R. Now we are trying to find the voltage across this 12 ohm resistor, which is 5.40 volts. So V will be unknown. Current is what we've already found, or in fact, we can read it from the ammeter. It is 0.45. And if you remember, this fraction was 9 upon 20. So 0.45 itself is 9 upon 20. Now let's multiply it by this resistance, which is 12 ohms. Now I'm going to cancel this with 4 3 times and with 4 5 times. And this is 27 divided by 5, and 27 divided by 5 is 5.40. You can do the same for the other resistor, and this basically helps us in understanding why voltage differs. That is the end of concept 3. Thank you.